Bismillahirrahmanirrahim. My name is Dr. Abdus Saboor. I am Associate Professor in Mathematics at Institute of Numerical Sciences, CUST. The title of this course is Special Functions 1. This is designed for the graduate students. The title of the topic is the Hypergeometric Functions. Prior knowledge. First of all, we will discuss some topics from the undergrad course, Complex Analysis, which will be uh, used in the next slides, and also few topics from the previous chapters of this book. I am following the book of the special function book of the Ranvelli, and also we will use the book of the Askew al. These both books are the standard books for the special functions. So first of all, we start from the definition of analytic function. The first definition, a function f of z is said to be analytic in a region R of the complex plane if f of z has a derivative at each point of R and if f of z is a single value. So this definition is about the function. That function is analytic in some region R of a complex plane if that function f of z has a derivative at each point of R and if that function is single valued. So if the function derivative exists at each point of that R region R, and if that function is single valued, then we will say that the function is analytic in this region. The second definition is about the point, that a function f of z is said to be analytic at a point z if z is an interior point of some region where f of z is analytic. So uh, if we have a point z and the function is analytic at that point z, so it will be analytic if the function if the z is an interior point of some region where f of z is analytic. Means uh, the function should be analytic at that point and also the neighborhood of these all points. So then we will say that the function is analytic at point z. Contour integral. Contour integration is a method of evaluating certain integrals along paths in complex plane. Contour integration is closely related to the calculus of residues, a method of complex analysis. So I will recommend all the students please go through the contour integral in complex analysis in detail so that you can understand. Pochhammer symbol is defined by this two brackets and the alpha and then subscript n, which is equal to alpha into alpha plus 1, alpha plus 2, alpha plus n minus 1, n greater than equal to 1, and alpha not equal to 1 if alpha not equal to 0. The function, this Pochhammer function, is called the factorial function, and it is an immediate generalization of elementary factorial since n factorial equal to 1n. We have discussed studied this topic in the previous chapter of this book. I am following the special function book of Ranvelli, and also we will follow the book of Asker et al. These both are the standard books of special functions. They are available online, and I have also emailed these books to the registered students in the beginning of the class. Gamma and beta functions are respectively defined by gamma z equal to integral of 0 to infinity e raised to power minus t raised to power z minus 1 into dt, where real of z greater than equal to 0. The beta function is 0 to integral of 0 to 1 t raised to power u minus 1 into 1 minus t raised to power v minus 1 into dt, where real of u greater than 0 and real of v greater than 0. Relation between Pochhammer symbol and gamma function. If alpha is neither 0 nor a negative integer, then alpha n equal to gamma of a alpha plus n divided by gamma of alpha. Relation between beta and gamma function. Beta xy equal to gamma x gamma y divided by gamma of x plus y. And similarly, Legendre's duplication formula is defined by this way, that square root pi into gamma of 2z equal to 2 raised to power 2z minus 1 into gamma z into gamma z plus 1 over 2. So these all definitions, they have detailed proofs available in previous chapters. We have already studied them, so please go through them again, recall them, and then go through the next slide. Now, come to the current topic. Almost all of the elementary functions of mathematics are either hypergeometric or ratios of hypergeometric functions. Series summation Cn is hypergeometric if the ratio Cn plus 1 divided by Cn is a rational function of n. Many of the non-elementary functions that arise in mathematics and physics also have representations as hypergeometric series. There are three important approaches to hypergeometric functions. First one is the Euler's integral form leads easily to derivation of essential identities and transformations of hypergeometric function. A second order linear differential equation satisfied by hypergeometric function provides a second method. This equation was also found by Euler and then studied by Gauss. Later, Riemann observed that the characterization of second order equations with three regular singularities gives a powerful technique involving minimal calculation for obtaining formulas for hypergeometric functions. Third one is the Born's integral. Born expressed a hypergeometric function as a contour integral. So some integrals that arise here are really extensions of beta integral. Beta function. This is the integral representation of beta function. So they also appear in the orthogonality relations for some special orthogonal polynomial. We will discuss this topic in next chapters, inshallah. There are some other polynomials, that Laguerre polynomial, orthogonal polynomial, and some other polynomial. We will study them in later chapters. The Gauss hypergeometric function. In the study of second order linear differential equations with three regular singular points, there arises the function f of a, b, c, z equal to this series for c neither 0 nor a negative integer. So here you can see that there is a comma between a and b, and then semicolon between b and c, and then semicolon between c and z. So what it shows, the comma between a and b means these both are the numerator parameters. Then the semicolon and c means this is the denominator parameter, and then semicolon and z means the argument of this function. So the left hand side is the function, and the right hand side is the series. The notation alpha an is called Pochhammer symbol or factorial function. This is already defined in previous slide. A mild variation of the notation f of a, b, c, z is often used. It is this one, like here, these are the two numerator parameters. These are written above. Denominator parameter is written below, and then argument is written over here. So one can use the previous definition or the previous notation or this notation. So this notation only reflects that it's only convenient for printing. The numerator parameters a and b are above the denominator parameter c, thus making it easy to remember the respective roles of a, b, and c. And this right hand side is the same series. The series on the right is called hypergeometric series, and the function on left is called hypergeometric function. Although Euler obtained many properties of hypergeometric function, but detailed study on this function is made by Gauss. That is why it is called Gauss hypergeometric function. Here is the theorem. If absolute value of z is less than 1, and if real of c greater than real of b greater than 0, then the integral representation of this Gauss hypergeometric function can be written in this form. So proof, if n is a non-negative integer, we can write this Pochhammer bn divided by Pochhammer cn, uh, this one, the Pochhammer bn divided by Pochhammer cn. So we are taking the series form. We are taking from the series form of this hypergeometric function. So we have discussed in the earlier slide that the Pochhammer symbol is equal to the gamma of b plus n divided by this gamma of b, and similarly Pochhammer symbol Cn equal to gamma of c plus n and divided by this gamma of c. So here we are multiplying and dividing the factor gamma c minus b. We know that if real of p greater than 0 and real of q greater than 0, then the beta function equal to this gamma representation, gamma p, gamma q divided by gamma p plus q. We have already discussed this in the previous slide, and you can also study its proof from the previous chapter. And the integral definition of beta function, that is gamma of b plus n, gamma of c minus b divided by gamma of c plus n, is equal to this one. This is the integral definition of beta function. Therefore, for absolute value of z less than 1, f of a, b, c, z equal to, here we are putting the values in the series, this series, this series, we are putting the values which we have obtained. So we get this one. Uh, Here we can interchange this summation with this integral, like we have interchanged it over here. This is only possible if the integral, this series is uniformly convergent in the same interval. So here you can see that the absolute value of z less than 1 means this interval and this interval is same. So that's why we can interchange, otherwise you can't interchange. The binomial theorem states that 1 minus y raised to power minus a is equal to this series, which can be written in this form. You can see this is the Pochhammer symbol representation, that a into a plus 1 into a plus 2 up to a plus n minus 1. So we have written over here the Pochhammer symbol. Put y equal to zp, and equation second becomes this one. This is the proof of this theorem. Second theorem, if real of c minus a minus b greater than 0, and if c is neither 0 nor a negative integer, then f of a, b, c1 equal to this one. This is very important theorem, and it will be used in next several derivation of several theorems in next slides and next chapters, and including this chapter. Since real of c minus a minus b greater than 0, we may write f of a, b, c1 equal to this. Here we have replaced z with 1. So here the argument z is removed. If we also stipulate that real of c greater than real of b greater than 0, it follows from the technique of theorem 1 that f of a, b, c1 equal to this. We have just put the value of z equal to 1 in the previous theorem. So we get this one. Therefore, if real of c minus a minus b greater than 0, and if real of c greater than real of b greater than 0, and since c is neither 0 nor a negative integer, f of a, b, c1 equal to this. So this is the integral form of a beta function. So we can write it in the form of this gamma functions, and then just simple steps, and we get this one. The value of f of b c1 will play a vital role in many of the results to be obtained in this and later chapters. Show that if real of b greater than 0 and if n is a non-negative integer, then f of this minus 1 over 2 n, minus 1 over 2 n plus 1 over 2, b plus 1 over 2, 1 equal to this representation. Here we have replaced a with this, b with this value, c with this value, and z equal to 1. So by theorem 2 we get just replace the values of a, b, c, and z in the previous theorem. So we get this one. After simplification we get this. The Glender's duplication formula for the gamma function yields gamma of b into gamma of b plus 1 over 2 equal to this. This is discussed in the second slide of this this video. Similarly, if we can also write the product of these two gamma function in this form. These both are the representation of Legendre's duplication formula. Therefore, f of this is equal to this one, and after simplification we get this is the desired result. So these are the references which I have used in these slides, but like I have in the beginning I told you that I am following these two books, the Renveli book and this sorry, I told SK et al. It is Andrews et al. Uh, published in 1999, and this is 1960, but its second volume was published in 1985. And this is the complex analysis book, complex variable and applications, a standard book uh, followed at undergrad level. But there are other books available. You can take help from the several books. Thank you very much.